Alright, we're going to talk about acids and bases today. First thing is the properties of acids. There are many characteristics of acids, and these are the top 5 that I want you to know. First off, they have a sour taste, such as lemons and Sour Patch Kids. Those have citric acid in them, and that's what you're tasting when you eat all of those sour candies. The next is that acids change the color of pH paper red. Some acids will react with metals to release hydrogen gas. You've seen that before when we did the hollow penny lab, and then again when we did the bark test for hydrogen, and we ignited it and it made that popping sound. Then number 4, acids will react with bases to produce salts and waters. You should know that already from our predicting reactions unit. And then some acids will conduct electricity, and that's because acids are polar molecules. So some will conduct electricity better than others because they are more polar than other molecules are. Okay, so some common industrial acids that you might see in the future if you work in the industry. Sulfuric acid is used in car batteries. Nitric acid we use in explosives and rubbers and plastics and dyes. Phosphoric acid is in most of the sodas you drink and in fertilizers. Hydrochloric acid is how we regulate swimming pool pHs, and acetic acid is regular household vinegar, although this is way diluted from regular acetic acid. They're also they can act as fungicides, which means they'll kill a fungus, and then we use them to help us synthesize other chemicals by making them give up their hydrogen, their protons. Now, what does that mean? Why did I equate hydrogens with protons? If we write an acid, let's say we write hydrochloric acid. Remember, this is polar, so the hydrogen is going to have a partially positive charge, and the chlorine is going to have a partially negative charge. When we force this to dissociate in water, then we will get them as ions. So we'll have the hydrogen ion over here, and we'll have the chloride ion over here. This right here, sometimes we say that an acid has given up a proton. It really hasn't, but it acts as though it has because this is a +1 charge right here, and that's the charge on a proton, +1. So sometimes you'll see or hear an acid being referred to as a proton donor, and that's because of this right here. Okay, the next thing I'm going to talk about are the bases. They taste bitter. Some examples would be mustard. Is basic and it tastes bitter, and then most medicines have a bitter taste because the active ingredient is a base. Number 2, bases change the color of pH paper blue. Bases will feel slippery to the touch. That should indicate to you that soap has base in it. And bases react with acids to produce salt and water, we know that, and then bases also will conduct electricity, and again, that's because they're polar. Alright, well, there have been several different ways of looking at acids and bases that have been developed over the years. The first one that we're going to talk about is Arrhenius acids and bases. And that says that acids are things that will generate these hydrogen ions in a solution, and bases are things that generate these hydroxide ions in a solution. So here's the general equation here. An acid plus a base gives us salt and water. We know that already. Here's kind of an example real-world situation. Hydrochloric acid plus sodium hydroxide will give us sodium chloride and water. Remember, when we were doing our predicting reactions section, we said that water could be written as HOH to help us doing our double displacement reaction. So what happened here is this hydrogen switched spots with this sodium in a double displacement reaction, so that we have hydrogen being donated from HCl, and this NaOH is going to leave an OH or hydroxide ion by itself. Then the positive hydrogen is going to match up with the negative hydroxide ion. So according to the Arrhenius way of looking at acids and bases, this must be the acid because it gave up or generated an H plus ion, and this must be the base because it generated an OH anion. Okay, so the strength of an acid and a base. Remember, we've talked about strong acids before back when we did our solubility rules. Strong acids will completely ionize in a solution, meaning that they will fully separate into cations and anions. Okay, so a strong acid is therefore an electrolyte, and that's why it will conduct electricity. The polarity of the acid increases as the strength increases. And then that means that it's going to be harder to overcome any hydrogen bonding intermolecular forces the stronger the acid you have. Acids that are weak electrolytes are weak acids. A strong base is a strong electrolyte for much the same reason as strong acids are strong electrolytes, because of their polarity. Please do not confuse an acid or a base's concentration with its strength. Remember, concentration we had two different ways of looking at so far. We've got molarity and molality, and so one of them is how many moles of solute there are per liter of solution. The other one is moles of solute per kilograms of solvent. So it's how much stuff do you have dissolved into how much solvent, essentially. That has nothing to do with the strength. The strength is whether or not it will completely ionize or whether it will not completely ionize. When a strong acid or a base is reacting in water, the reaction will go to completion, meaning there is no equilibrium established, so you will not use the forward and backward arrows in that situation. Okay? When we say that it completely ionizes, that means that it goes all the way to the end. There is no initial acid left over. So if I go back to our equation here, let's say that I am dissociating hydrochloric acid in water. We will form 100% of the hydrogen ion here, and we will form 100% of the chloride ion. And at the end, there's none of this left over. Now we only have these. And I should go ahead and put in here that these are aqueous because those are now distributed out in the water. Okay? Alright, if we have a weak acid or base that reacts in water, then yes, we will have an equilibrium that forms, and it will form such that it favors the reactants more than the product, so we will still have some of the weak acid hanging around at the end of that dissociation. How do you tell the difference between a strong acid and a weak acid, and a strong base and a weak base? You go back to your solubility rules. Okay, remember, these are the strong acids here, and any acid that has 2 or more oxygens than hydrogens are all strong. And then everything else, including organic acids, are weak. Remember, organic means that it's carbon containing. Alright? Then our strong bases would be anything that we make a hydroxide out of that also has group 1A. And then all the hydroxides of calcium, strontium, and barium are strong too. All the other hydroxides are weak bases. Okay, the next way of looking at acids and bases is using the Bronsted Lowry method. The Bronsted Lowry acid says that it's anything that will donate an H+. In other words, being a proton donor. And the Bronsted Lowry base is anything that will accept an H+, or be a proton acceptor. Okay, so here's the normal equation, or the general equation for a Bronsted Lowry acid-base reaction. We have an acid and base on this side, and we have another acid and base on this side. One of the acids will be stronger, one of the other acids will be weaker, one of these bases will be stronger, and the other one will be weaker. So here's kind of an example. So here we have nitrous acid, and it is going to dissociate in water, and so we will form the nitrite ion and a hydronium ion. Now, we are going to form what are called conjugate acid-base pairs, okay? So each acid will have a conjugate base, and each base will have a conjugate acid. And that just kind of means a partner when we say conjugate. Now, these conjugate pairs are only going to differ by a proton, or in other words, an H plus ion. Okay, so in this example, we have the nitrous acid functioning as the acid, and we have water functioning as the base. Remember, in a Bronsted Lowry acid-base reaction, the acid will donate the hydrogen ion, and the base is the thing that accepts it. So if you look here, you'll see how H3O plus was created. What happened was the oxygen here of the water reached out and snatched that hydrogen off of the acid. So it accepted this hydrogen ion, and by doing so became the hydronium ion. So here's what that would look like if we looked at our Lewis structure. We have these electron areas on the oxygen, and those are going to be attracted to the positive charge of the hydrogen ion here that would be attached to the whole acid, but we're just looking at the hydrogen part of it. So this negative charge is attracted to that positive charge. So we're going to reach out here and attach ourselves to that hydrogen. And so we're going to form our hydronium ion. Now what happens is we attached this one other hydrogen here, so we used an electron pair in order to create another bond, and we're left with one lone pair of electrons. If we look at the formal charge of oxygen here, we've got 1, 2, 3, 4, 5. Oxygen's got 5 valence electrons, and it's supposed to have 6. That means that the oxygen is the one responsible for the overall charge of the hydronium ion. The formal charge of oxygen is +1, and that's where we get the +1 charge on the hydronium ion. So when we write it as the H3O plus, it is the oxygen that actually carries the plus charge. Alright, so that means that the nitrite ion is going to be the conjugate base, and the hydronium ion is the conjugate acid. So right here, each acid has a conjugate base, and it differs by a proton. So when this acid here lost the proton, it leaves behind the conjugate base, which is this, NO2 with a minus charge. So that's why this is the conjugate base. And then the water functioned as the base. Once it accepts the hydrogen proton here, it forms the conjugate acid. So wherever that hydrogen proton goes, that's what becomes the new acid. So here's kind of another generalized Bronsted Lowry equation. HA is going to be our acid. Water will function as the base this time. Again, the oxygen from the water grabs onto the hydrogen on that acid and creates the hydronium ion, and leaves A minus by itself. That means this is going to function as the conjugate base, and the hydronium ion will function as our conjugate acid. Okay, there are many different kind of classifications of acids that we can talk about, and they all have to do with how many hydrogens do they have. So we have what's called a monoprotic acid. Mono for one, prot for that proton. Alright, so here HCl has one hydrogen, which would function as one proton it would give up. So this is what's called a monoprotic acid. Then we have a diprotic acid, di meaning 2. So that means this one will donate 2 hydrogen protons, or 2 hydrogen ions. So here we have carbonic acid. And then we have polyprotic acids, and those are going to be anything that will donate more than 2 hydrogen ions. So here we have phosphoric acid as our example, and it's going to be able to give up 3 hydrogen ions at a time. And that's a very important thing to note. It doesn't give up all 3 at once. It gives them up individually one at a time, and so does the carbonic acid, and so does the hydrochloric acid for that matter. Alright, so here's a quick summary for us. The Arrhenius acids are going to produce these hydrogen ions, and they're going to produce hydroxide ions for an Arrhenius base. A Bronsted Lowry acid will be a proton donor or a hydrogen ion donor, and a Bronsted Lowry base is a hydrogen ion acceptor. Okay, so how do we decide what the strength of the conjugate acid and base will be? Well, that's going to depend on what the original acid and base were. For example, hydrochloric acid is a very strong acid. That means that it's going to give up protons, in other words, hydrogen ions, readily. It follows then that the Cl- that it leaves behind has very little tendency to attract or keep a proton. If it's giving it up so easily, that means it doesn't have the ability to hang on to it. Therefore, the Cl ion must be an extremely weak base. Of course, we're using the Bronsted Lowry definition. Remember, the Bronsted Lowry base is a proton acceptor. That means that it's something that is going to take a hydrogen proton. So if this Cl- is not able to hang on to a hydrogen proton, it's definitely not going to take one. That means that this is a very poor Bronsted Lowry base. So here we have a strong acid. Water is going to act as our base. This would be our conjugate acid, and this would be our conjugate base. Our conjugate base is going to be very weak in this case. Now we have two ways of writing this dissociation reaction. You can write it so that water is one of the reactants, and I would suggest that because it shows that we have an acid base and then another acid base here, which follows the general formula for Bronsted Lowry acid-base reaction. Or you can, if you're more interested in just talking about the proton transfers or the ionization here, we've got water over the reaction arrow so that we can say, yeah, it's in the beaker, but what's really happening is the dissociation is occurring, and we've got these ions that are forming. Because sometimes we will talk about acids with H plus, and sometimes we'll talk about them with H3O plus. Your book uses this, so we're going to use this a lot of the time, but please remember, this is not real. That doesn't really exist in nature. It forms a hydronium ion, and that's what really is functioning as the acid. Okay, so we can draw a conclusion from our example up here. The stronger the acid is, the weaker the conjugate base it forms. So hydrochloric acid is one of our strong acids according to our solubility rules. And here's the conjugate base that partners up with it. And this is a very weak base. So strong acid forms a weak conjugate base. And likewise, the stronger the base is, the weaker the conjugate acid is. So here, water is functioning as a base. But remember, water is neutral. It's 7 on the pH scale, so it's actually a weak base. That means it's going to form a strong conjugate acid. So the opposite of these statements are also true. The weaker an original acid is, the stronger the conjugate base would be. So they kind of can go hand in hand with each other there. Okay, so what that allows us to do is to predict the strength of not only the acid and base, but also the conjugate acid and conjugate base just by looking at our beginning reactants. So here we have perchloric acid. Notice it's got 2 or more oxygens and hydrogens. That makes it a strong acid. Once again, water is having to function as the base. Remember, I said just a second ago, water is neutral. It's 7 on the pH scale. The cool thing about water is that it can function as an acid or a base. According to the Arrhenius method of acid bases, an acid is something that can donate a hydrogen proton. Water can do that. An Arrhenius base is something that can generate a hydroxide ion. Water can do that. That means that water is both an acid and a base at the same time. Now, which one of them it's going to behave like is actually dependent upon what it's paired with. So here it's paired with a really strong acid. This is going to be way more likely to give up hydrogen ions than water is. That means water is going to be forced to behave like a base this time because it was paired up with a much stronger acid. Since this is so strong, that means the conjugate base over here is going to be very weak. From the moment that this reaction starts happening and we start forming these hydronium ions, that means these two acids here are going to be in direct competition with each other to see who's going to give up the hydrogen proton first. This is much stronger than the hydronium ion is. That means this one is going to be the one giving up all of the hydrogen ions to the water to form this. So this reaction arrow here, you'll notice, points all the way to the product side, because there will not be any more of the acid left over at the end of the reaction. This goes to completion. So this is the weaker acid, this is the stronger acid. Since this is such a stronger acid, it means water is going to function as a strong base, and that means this is going to be the weaker base. And remember, the stronger the base is, the weaker the conjugate acid. So since water is being forced to act like a very strong base, meaning it's having to accept a lot of these hydrogen protons, it's going to form a very weak conjugate acid. In this next example, we have a weak acid dissociating in water. This is acetic acid, or as you know it, vinegar. And when we put it in water, it functions as a weak acid, as we predict because of our solubility rules. And that means that the hydronium ions that are already present are actually functioning as a stronger acid than the acetic acid is. So this is the strong acid here. And since this is the weak acid, that means water is having to function as a weak base. It is not accepting the protons from the weak acid. It is actually the base down here, the acetate ion, that is receiving the protons from the hydronium ion instead. That means that the reaction is heavily favored towards the reactant side, because when these two things react, they generate the reactants, okay? So again, we have our pairs. We have a weak acid forming a strong conjugate base, and we have a weak base forming a strong conjugate acid. Okay, the acetate ion is functioning as a better proton acceptor than the water is, and the hydronium molecule is acting as a better hydrogen proton donor than the acetic acid is. Something interesting to note is that in both reactions, examples 1 and 2 that I just showed you, the favored direction of the reaction is towards the weak acid and weak base, okay? So the second conclusion that we can draw here is that the proton transfer in these acid-base reactions will favor the production of a weak acid and a weak base, rather than the production of a strong acid and a strong base. This chart comes from your textbook, and it gives us a list of our acids, their formulas, our bases and their formulas, and what their strengths are in relation to each other. So on the acid side, the strength increases as we move up, and then here are the ones that are classified as strong acids. That's the hydrochloric, hydrobromic, hydroiodoic, and then acids that have 2 or more oxygens than hydrogens. So one to kind of note here is that the hydronium ion concentration is just under the strength level of sulfuric acid. Remember, that's battery acid. That's a very strong acid, which means that the hydronium ion itself must indeed be pretty strong. Okay, over on the base side, the weak bases are up here at the top, and we increase in strength as we go down. So just as we expect, these are the weak bases. These are the conjugates of these strong acids. Remember, strong acids form weak bases. So these are very weak indeed. They don't tend to hold on to the hydrogen ion very well at all. And conversely, down here, these are going to hold on or attract it even more, because these are the conjugate bases of these weaker acids. So acetic acid is weak, and therefore it's going to make a stronger base. So here you'll see the hydroxide ion is pretty strong, and this one right here is a special one to note. That's the hydride ion. That's actually a hydrogen ion that's been forced to have a negative charge instead of a positive charge, and so it acts as a very strong base. And that's because hydrogen doesn't like to be negative, it wants to be positive, so it is ready to attack basically anything in order to share that electron and get rid of that negative charge. Okay, we've talked about neutralization reactions before. Remember, that's an acid plus a base giving us salt and water. It's a double displacement reaction. It's just a special kind that we call a neutralization reaction because it forms water, and water is neutral on the pH scale. What we haven't talked about yet, and we will definitely get into this, although it will be a little bit later admittedly, is that when the salt forms, the salt can be a neutral salt, it can be an acidic salt, or it can be a basic salt. Depending on what salt you create, it can actually help add to the acidity of the reaction, or it can add to the basicity, or it's just neutral. Sodium chloride happens to be a neutral salt, and it doesn't affect the pH of the reaction very much at all. Okay, so now we're going to start talking more about pH and about a special chemistry skill that we're going to do in lab called titration. First off, we need to talk about the autoionization of water. Auto means to do on your own without any help, and ionization means to create ions. So here we have two molecules of water. Okay, the red is the oxygen and these two white ones are both the hydrogens. We have an equilibrium situation that's established. Now, because of hydrogen bonding, the oxygen from one of these water molecules is attracted to the hydrogen of another. And we have obviously in a container more than just two molecules of water, but that's all I've got to show you right now. So what happens is this oxygen, through hydrogen bonding, attracts this hydrogen towards itself. Eventually, it will sever the bond between this oxygen and hydrogen over here and add a hydrogen to this oxygen, which will create a hydronium ion and a hydroxide ion. Now that only lasts for a fraction of a second. It's like a trillionth of a second. Let's take a look at that via computer simulation.
Each water molecule has one oxygen atom and two protons attached by covalent bonds. Neighboring water molecules interact through hydrogen bonds, exerting electrostatic forces of directional adhesion responsible for many of water's peculiar properties. This movie focuses on dynamics occurring along a wire of such bonds, highlighted with color. Keep in mind, however, that these motions are driven in large part by what's going on in the environment of surrounding molecules. As dynamics proceeds from this initial configuration, protons will move along the highlighted wire, and colors of the water molecules will change to help us resolve where protons are moving. Blue coloring highlights the hydroxide ion, an oxygen atom bound to just one proton. The yellow oxygen atom is bound to 3 protons. That's a hydronium ion. Let's see that again. The initial movement of protons along the wire is prompted by a rare fluctuation in voltage, produced by an unusual arrangement of surrounding molecules. Its structural basis is collective and too subtle to pick out by eye. The important thing is that the voltage is transiently large enough to destabilize an OH chemical bond. The voltage fluctuation does not last long, not even a tenth of a trillionth of a second. In the rapid charge separation it spurs, each participating molecule along the wire seizes a new proton from one neighbor and relinquishes another proton to the opposite neighbor. If nothing else happens, this collective proton translocation will proceed in reverse as the voltage fluctuation disappears, leading back to the ion-free state. What does happen in this trajectory to fix the charge separation is a change of allegiance of hydrogen bonds. Let's see that again. The hydrogen bond wire breaks, blocking the original route for recombination. Different routes along other connecting wires are available, but they are less passable. Separated charges can now diffuse apart even after the transient voltage disappears.
Okay, so hopefully that makes a little bit more sense to you now. This is the most fundamental acid-base reaction there is. Remember, I told you water is neutral and it has both parts. It's got an acidic hydrogen and it's got a hydroxide group. So it can function as both an acid and a base and it does that by switching between the two very quickly, and that process is called autoionization. Now that we're talking about equilibrium reactions, we're going to introduce a new concept called an equilibrium constant. All constants in chemistry are symbolized with a K, and then they usually follow with a subscript that indicates what kind of constant we're talking about. So we're going to talk about Kw, which is the equilibrium constant of pure water while it's going through autoionization. Here's how you do it. The equilibrium constant of the autoionization of water is equal to the concentration of the hydronium ion times the concentration of the hydroxide ion. Now up here I've written hydroxyl. This YL is an ending that comes from organic chemistry, and we're not going to get into that so much, so just understand that a YL ending is letting you know that that's just a piece of a molecule and it's really attached to a larger molecule. So both of these together are going to equal 1 times 10 to the negative 14th molar squared. Now the 14th here is because the pH scale goes all the way up to 14. Alright, let's identify what the variables are here. These brackets that you see around the hydronium ion and the hydroxide ion, those indicate concentration, and they indicate it in units of molarity, which remember are moles of solute over liters of solution. Kw is of course our equilibrium constant for water, and its units are molarity squared because this concentration is in units of molarity and this concentration is in units of molarity. So molarity times molarity is molarity squared. Okay, a calculation of the equilibrium constant can actually give us some information about a reaction. If you calculate the equilibrium constant and it comes out as less than 1, then that means that the reaction prefers to stay on the side of the reactants, so it favors the reactants. Remember, reactions of acids and bases that favor reactants are the ones that start out with weak acids and weak bases, because the reaction always favors the production of a weak acid and a weak base. In the case of the autoionization of water, it will be less than 1 because water likes to stay water rather than ionizing into hydronium and hydroxide. Since water hardly ionizes at all, it's a poor conductor of electricity. I know that a lot of times you hear if it's raining or lightning, the kids have to get out of the pool and you don't want to be around liquid because you could get electrocuted. Now all of that's true, but if I were to get a perfectly clean glass container and I filled it with distilled water, that's water that's had all of the ions removed from it, and I put you in that water, I had you stand in it barefoot and your feet had been totally clean, and I put you in that out in the middle of a lightning storm and lightning struck the water, you probably would not get electrocuted because water itself, pure water, doesn't really conduct electricity that well. You have to have some ions in it. If I poured salt in that water and the sodium chloride broke apart into their ions and then the lightning struck it, you'd be in for a bad day. Alright, let's talk about pH. This lowercase p here stands for the log of something, and the something that it's taking the log of is the next thing that follows. H is standing for the hydrogen ion concentration or the hydronium ion concentration. Now I've repeated to you several times that water behaves like an acid and a base, and that has a special name. It's called amphoteric. So we could say that water is an amphoteric molecule because it behaves like both acids and bases. So the acidity of a substance is defined by its pH value typically, and the basicity of a substance is defined by the pH as well. Alright, so here we had that P that stands for log, and H is telling us the log of what? So pH is going to be the negative log of the hydronium ion concentration. So this is the logarithmic form of the equation here, okay? Well, hopefully you remember from algebra that if you've got a logarithmic form, you can switch it into the exponential form. So this is the exponential form. The hydronium ion concentration is equal to 10 to the negative pH. This is a log base 10 right now. So if we want, and that's what your calculators are set up for, we could write that as log base 10 of the hydronium ion concentration. So the exponential form, remember, you move this piece out front and then you raise 10 to the power of the pH. Notice that at equilibrium, the concentration of the hydronium ion is going to be at 7 because 7 is neutral on the pH scale. So we're splitting the concentration of the hydronium ion and the hydroxide ion evenly so that we end up with a neutral pH. So indeed, water would have a pH of 7 because the hydronium ion concentration would be this figure here, 1 times 10 to the negative 7. We have another type of measurement that we could make. It's called pOH. So rather than taking the negative log of the hydronium ion concentration, we can take the negative log of the hydroxide ion concentration and find out what we call a pOH. This gives us an idea of the acidity of a solution or the basicity of a solution. Notice that a high pOH means the solution is acidic, while a low pOH means the solution is basic. This is exactly the reverse of the pH scale. Remember, on the pH scale, having a low number indicates acidity, and having a high number indicates basicity. Let's take a look at these formulas, and yes, you do need to memorize all of them. We've got the pH formula, which is the negative log of the hydronium ion concentration. The pOH formula is the negative log of the hydroxide ion concentration. If we have pH plus pOH, it will equal 14. Remember, that's the max of the pH scale. The hydronium ion concentration is equal to 10 to the negative pH, and the hydroxide ion concentration is equal to 10 to the negative pOH. You do need to know all of those. There are some links here, okay? The pH scale is linked to the hydronium ion concentration, and the pOH scale is linked to the hydroxide ion concentration, and then the one in the middle links them all together because it includes both of them. Alright, so if you kind of remember these in pairs, then you'll be okay. Alright, let's see if we can work an example question. What is the pH of a 1.0 times 10 to the negative third molar sodium hydroxide solution? Now remember, sodium hydroxide is a strong base, okay? Remember, hydroxides of group 1A are all strong. That means that this will completely dissociate in water and become ions. So we'll have the sodium ion and the hydroxide ion. Also, notice that they're 1 to 1. For every 1 mole of sodium ions that get created, 1 mole of hydroxide ions will get created as well. And we were told that we have a 1.0 times 10 to the negative third molar sodium hydroxide solution. That means that this many moles of sodium ions will be created, and this many moles of hydroxide ions will be created. Now let's find the pH. Remember, the pH is equal to the negative log of the hydronium ion concentration. Also remember that the hydronium ion concentration multiplied by the hydroxide ion concentration is equal to 1 times 10 to the negative 14th molarity squared. Now we can use this to our advantage. Remember, we want the pH. So if we know what the hydroxide ion concentration is, then we can figure out what the hydronium ion concentration is. So we will divide by the hydroxide ion concentration on both sides, as we've done here. We'll take the 1 times 10 to the negative 14th molarity squared divided by 1 times 10 to the negative third molar, and we end up with 1 times 10 to the negative 11th molar for our hydroxide ion concentration. And we're not done yet. Remember, we were asked about the pH, not the concentration of the hydroxide ions. So we need to plug into our pH formula. So we'll take the negative log of the hydroxide ion concentration that we just figured out right here, and we end up with 11. So we have a pH of 11, and that makes sense because remember, numbers above 7 on the pH scale indicate basicity, and we know that sodium hydroxide is a base because anything with hydroxide is a base. Okay, here's an additional question. What is the pOH of the above solution? At this point, there are two ways to figure that out. We can either plug into the formula for pOH, which is the negative log of the hydroxide ion concentration, or we can use a different formula that involves the pH and the pOH in order to solve for the pOH. Remember that pH plus pOH is equal to 14, and we just calculated the pH, so we know what this is, we know what that is. That means by simple subtraction we could figure out what the pOH is. So we know the pOH is going to be 14 minus the pH. So we'll say 14 minus the 11 that we calculated, and we get a pOH of 3. Remember, low numbers on the pOH scale indicate basicity, so this is right where we expect. Okay, here are a couple of practice questions, and I want you to try these on your own as best as you can. Remember our cloud. This has all of the formulas in it that you could possibly need to do your pH calculations, so use those to answer these practice questions. What is the pH of a solution if the hydronium ion concentration is 3.4 times 10 to the negative 5th molar? And this one, determine the hydronium ion concentration of an aqueous solution that has a pH of 4. Okay, so here we have calculated the pH. It's the negative log of the hydronium ion concentration, and we end up with 4.5, and that's with the correct number of sig figs. We had 2 in the given, so we need 2 in our answer. And then here, to determine the hydronium ion concentration, remember it's 10 raised to the negative pH. The pH they gave me was 4, so that's 10 to the power of negative 4. That's the same as 1 times 10 to the negative 4. And so molarity is the unit there because it's a concentration of hydronium ion. Alright, hopefully you came up with the same things as I did. Okay, the last topic in our acids and bases section is going to be titration. A titration is simply adding a certain concentration of a known solution to an unknown concentration of another known solution. And we're going to try and find what we call the equivalence point, and that is the exact place when the two solutions have exactly the same concentration. The end point indicates when you reach the equivalence point, okay? And it will be the point at which an indicator changes. This indicator is usually phenolphthalein. Now, of course, that's the indicator for acid-base titrations, which is what we're talking about. There are other indicators for other types of titration. We're going to have what we call a standard solution, and that's the one that we know the concentration of. And then we're going to have a primary standard. And this is kind of the control that we have in an experiment. Remember, a control is something that we compare back to so that our results have meaning. Well, this primary standard is just a way for us to check the concentration of our known solution and make sure that it stays the concentration that we want it to be for every experiment that we do with it. Okay? Alright, so what is the importance of titration? Why would we ever need to use this? Well, the main reason is so that we can find out what the concentration of an unknown solution is. For example, if you go to the hardware store and you buy some acid there and you don't know what the concentration of that acid is, you could perform a titration on it to find out. And in fact, that's what I do a lot of the times for the chemicals in our lab. If I am running out of hydrochloric acid and I don't have time for the chemical supplier to ship me some, then I'll go buy a little bit less pure acid, and then I'll need to perform a titration on it so I know what concentration I'm getting from the hardware store, because their solutions are not standardized, so you're not going to get the same concentration every single time. So I can't assume that, and therefore I have to figure it out before we use it in the lab. Okay, so let's do an example together and learn the process of doing this titration, okay? The first thing that we need to do is to write our neutralization reaction. Here's our question. Suppose 20 milliliters of 5 times 10 to the negative 3 molar sodium hydroxide, so that's the base, is required to reach the endpoint in the titration of 10 milliliters of HCl of an unknown concentration. So we don't know the concentration of the acid here. Alright, so step one, we need to write that balanced neutralization reaction. Remember, neutralization reactions will form salt and water, and they're that special kind of double displacement. Okay, so here is our balanced neutralization reaction. We've got our acid, we've got our base, we've got the salt, and we've got water. Okay, the next thing we need to do is to calculate the number of moles of sodium hydroxide that got used up in the reaction. Okay, so here's how we do that. We're going to take our volume of the base and put that over 1. That's our given. Remember, molarity is a conversion factor, okay? It is a conversion factor between moles and liters, so it's not ever going to be the given, okay? So we've got our given here, where we know we can convert from milliliters to liters, and then we use the molarity of the base here as that conversion factor. 1 liter of our sodium hydroxide solution is equal to this many moles of sodium hydroxide. So we get our molar value for sodium hydroxide. Okay, now remember, the thing that we're trying to do is find the concentration of HCl, the acid. Okay, well, we already know the volume of HCl, and concentration, they're asking about molarity there. Okay, remember, molarity is equal to the moles of solute over liters of solution. I can change milliliters into liters, so what I'm really trying to find out right now is the moles of the acid, and once I do that, I'll be able to calculate the molarity. So we're going to use our stoichiometry to calculate the moles of the acid, because we just figured out moles of sodium hydroxide, and I've got a balanced chemical equation up here. Now, these are 1-to-1 molar ratios. So when I take the moles of the sodium hydroxide and then I use the balanced chemical equation and go from moles of sodium hydroxide to moles of hydrochloric acid, we're going to get the same molar value for the hydrochloric acid. Now we can just plug into our molarity formula to figure out what the molarity of the acid is. Alright, so we will convert the 10 milliliters into liters, and then we'll plug into our molarity formula. So here's the moles of the HCl solute, here's the liters of the solution, and here is the molarity, that unknown molarity of our hydrochloric acid, which is 0.01 molar HCl. Okay, so either way that you choose to write this, and I suppose here we're showing it with 2 significant digits, so we would need 1 more 0 there if we want that to be 2 sig figs. So either way, that is your final answer. Alright, let's do another practice question. Okay, in a titration, 27.4 milliliters of 0.0154 molar barium hydroxide, okay, notice that's got hydroxide, that means it's the base, is added to 20 milliliter sample of hydrochloric acid solution of unknown concentration. What is the molarity of the acid? Okay, just like we did before, you need to start with the neutralization reaction. Okay, then the next thing we need to do is to calculate the number of moles of this barium hydroxide that are in our solution. So we're going to start with the volume as our given. Okay, so we have figured out how many moles of HCl we have in our 20 milliliter sample, and now we need to know what the molarity of the HCl is. So we're going to plug into our molarity formula. Alright, so we converted our 20 milliliters of HCl into liters, and then we're plugging into our molarity formula, moles of solute over liters of solution. So we're going to take the moles that we got from our first calculation, and we actually need to use every single number that we got in the calculator, okay? Don't just use the 4.2. Use every number. And then we'll divide it by our volume, and this is what we get with the correct number of sig figs, which we have 3 sig figs, so we need 3 sig figs here. Of course, we could also represent this with scientific notation. Alright? You see if you can do this last one on your own. Okay, here's what we come up with. First thing we did was write our balanced neutralization reaction. Fortunately for us, it's all 1-to-1. Then we start with the volume of our base and convert that into moles using the molarity as a conversion factor. So we went from milliliters to liters and then liters to moles, and so here's the moles of our base. Now we're going to use stoichiometry to convert from base to acid. So we have our moles of our base that we just calculated here over 1, and then the balanced chemical equation says that 1 mole of base is equal to 1 mole of the acetic acid. So we have that here. That means we have the same number of moles of acid as we did base. Now all we have to do is plug into our molarity formula. They gave us 21.2 milliliters of our acid, so we do a little bit of dimensional analysis and convert that into liters so we can plug in. We take our moles of acid and divide it by liters of acid, and here we have our molarity of our acid, 0.157 molar acetic acid. So hopefully you came up with the same thing that I did. Alright, if you have any other questions about any of the acid-base section, please make sure you come and see me for tutorials and I'll be glad to help you with that. And as always, thanks for learning with me today. Bye.